Hello, I hope things are going well. We just have a quick video today to just look back over these examples that I skipped yesterday, and then to kind of put everything all together and hopefully give you some good time to just work on your assignment that's due today and the one that's due Friday. And yeah, hopefully just give you a little extra time back. So let's take a look at B right here. We have e to the alpha t cosine of omega t. And I hope you gave this one a try. And if not, just pause real quick and look it over and see if you can figure out what this one should be. So basically, this is a combination of two things right here. We have this function of t that's cosine. And then we have this e to the alpha t, which our table does tell us specifically how to deal with that, and we'll kind of come back to that in a second. But let's just look first at the Laplace of cosine of omega t. Oh, I guess I don't really need parentheses. Okay, and in the table, it specifies that this transform would look like s over s squared plus omega squared. All right, so the good news here is we don't really have to worry about what omega is. It's just some unknown. What we do have to worry about is bringing this e to the alpha t back in. So if we remember from yesterday, we were talking about how when we have an e to the alpha t, this shifts the argument of our transform function. So this right here, if we were just doing cosine of omega t, would be our transform function. But what this e to the alpha t does is this takes our transform, our argument from s onto s minus alpha. That's basically what we have. So if we are performing this all together, the Laplace of e to the alpha t cosine omega t, then that means everywhere that we have an s, we shift it to an s minus alpha. So that's going to give us s minus alpha in the numerator, and it's going to give us s minus alpha quantity squared plus omega squared in our denominator. And then this right here is our final answer. So a little similar to what we saw yesterday for example A, and that's kind of what I was hoping you would see if you worked that one out on your own, is that this just shifts the argument in our transform function. So then let's go ahead and take a look at this inverse Laplace transform. We are taking the inverse Laplace of e to the negative alpha s over s squared plus 1. So let's just go ahead and kind of take this apart like we did the inverse yesterday. We have an e to the negative alpha s here as well, and this causes a shift in the time domain. And so what I'm going to do is I'm going to just rewrite this as the Laplace of e to the negative alpha s times the function 1 over s squared plus 1. So that way we can look at this right here as being our function of t, f of t. And so if that's the inverse that I'm trying to perform, if I'm just doing the Laplace of 1 over s squared plus 1, s squared plus 1, this becomes my sine function. And in this case, omega would equal 1. And so this would give me sine of t. Simple as that. Okay. And I told you yesterday we're not going to worry about the fact that this shifts our t value, our time function, as well as the unit step function. We're not going to worry about the unit step. That's going to be the part that we remove ourselves from having to worry about, given that we're learning about it this way. So all we're going to do is we're going to kind of perform a transform like we did up here, and we're going to take our t onto t minus alpha, because here this negative alpha shifts my function to the right alpha units. Okay, and so what my function of t is going to look like, so putting this all together, I'll just bring it up here, is that I would get the sine, do this, the sine of t minus alpha. That's my f of t. Technically, my f of t minus alpha, if I take f of t and I shift it to the right. Okay, so again, we're not going to worry about our start point when it comes to the piecewise function. That's where the unit step function would come in. We're just going to worry about what our f of t looks like, or in this case, our shifted f of t. So let's put this together and talk about what this has to do with our differential equations. And I'd kind of preface that a little bit with how we need to know the second and the first derivative transforms. And so that's what we're going to look at. We are going to basically transform this into a capital Y of S transform function, and then we are going to solve for that. So we're going to figure out what that solution will look like. So the way we do this is we take the Laplace of the whole thing, y double prime minus 2y prime equals 2t squared minus 6, where essentially what we are doing is we are taking the Laplace of each individual term. So we take it of y double prime minus the constant 2. We can pull out our constants, 2 times the Laplace of y prime. On the other side of the equal, again, we're going to pull out our constant here of 2 times the Laplace of t squared. And then 6 itself is the constant. So we could say minus 6 times the Laplace of 1, because that is in our table. Okay, so this would be where we reference our table to complete all of these Laplace transforms we just laid out. So from the table, the Laplace of y double prime is s squared times capital Y of s. Sorry, my capital Y's are going to look weird. I just, my lowercase y's would look too much like the uppercase ones if I didn't do them weird like this. And that's my story, and I'm sticking to it. So continuing on, minus s of 0 minus 1. Where does that come from? Because I evaluated y prime of 0 right here, and it is equal to 1. So this is, if we evaluate, s of 0 right here, that's going to also eliminate. And so, and I actually wrote that wrong. It's f of 0 there, or in our case, lowercase y. Okay, so if we go off of the table, it will have f. We used y here. So let me go ahead and do this just to kind of make that clarification. Okay, so this y of 0 is equal to 0, so that eliminates, and we get 1 from this. So let me go ahead and bring it down. S squared times capital Y of s minus 1 is what we get there. Okay, now choosing a different color here, we're going to do 2 times the Laplace of y prime, which is going to be from the table s times capital Y of s minus f in the table. It's f. Let's go back to y of 0. Okay, which y of 0 again is 0, so that's going to just cancel out. And this gives me minus 2s capital Y s. So basically what we have here, and I wrote this with multiplication, it's probably a little bit better practice to just squeeze this together to s squared y of s and then minus 2s y of s, because basically we're going to take a look next at these like terms right here. Okay, but first I'm going to go ahead and just work on the other side of my equal. These are the ones, typically they're always going to be a little bit easier. So we're going to have 2 times the Laplace of t squared, which is going to be from the table 2 over s cubed. 2 over s cubed minus 6 times the Laplace of 1, which is 1 over s. And so over here, we are going to concern ourselves with, getting a common denominator so we can simplify and do all that good stuff. So first, let me go ahead and just bring it down as 4 over s cubed. And then we can go ahead and do this since we want a common denominator. We'll make that over s cubed as well. So it looks like we'll have minus 6s squared over s cubed. So like I said, we're going to go ahead and take a look at our common terms right here where we have a capital Y of s, and we are going to factor out the s squared minus 2s. So we're going to factor out our common factor of capital Y of s. That leaves us with just this minus 1 on this side, and then 4 minus 6s squared all over s cubed. Now let's just review our goal here is to solve for capital Y of s. That is our goal. And, and we'll kind of go, this is our goal for today. And then later on, our goal will be figuring out and solving for lowercase y of t, because that's obviously the solution for our differential equation. But for right now, this is just our concern, solving for capital Y. So what we're going to do is we're going to add the 1 over to this side. We're going to divide out the s squared minus 2s. That will get our capital Y of s by itself. So adding the 1 over leaves that s squared minus 2s times y of s. If I add 1, I'm basically adding s cubed over s cubed. Okay, so I'm going to have 4 minus 6s squared plus s cubed all over s cubed. And then I'm going to divide from both sides this s squared minus 2s. And that will clearly just get lumped in with my denominator here. So the simplest form of this, and really all we're concerned about leaving it, is capital Y of s is equal to 4 minus 6s squared plus s cubed all over s cubed times the quantity s squared minus 2s. At this point, like I said, not really concerned with getting it much more simple than that. We just want to know what capital Y of s looks like at this point, and we can take it a little bit further in our next section. But hopefully that was kind of a quick, easy way, and you can get a little more practice with this today.